I know I wasn't here on Tuesday when we last met. So if you guys have questions from homeworks 2 or the new one, homework 3, I'm happy to take a few minutes here and run through some of those if we'd like to do that. So again, if you have any homework questions that we'd like to kind of talk about before we get rip rolling into some new stuff, I'm happy to take a few minutes here and do some of that stuff on worksheet 1. Okay, I don't have homework 1 on here. So let's grab that then. Number 5?
Yeah.
Okay. So the 1575?
Yeah.
Okay. So I would start by doing a prime factorization. And if I look at 1575, it's pretty obvious to me that that's got to be divisible by 5 because it ends in a 5. So I can do like 5 and 315. And 315, again, pretty obviously is divisible by 5 because it ends in a 5. So I have 5 and 63. 63 is 7 and 9, and then 9 is 3 and 3. So I know that 1575 is, let's see, I have 1, 2 5s. So I have 5 squared. And then I have 1, 2 3s. So I have a 3 squared. And then a 7. So far, so good? Okay. I know for a square root, if I have something squared, like that's a number then that I can pull to the outside. So the 5 can come out. Same thing with the 3 can come out. The 7, though, isn't something squared, so that has to stay in. So I'm left with like 15 square roots of 7. Walter.
If you factor it differently, like different than 315 times 5, you will get a different answer?
No. So prime factorizations are unique. You'll end up with the same 5 numbers at the end, whether you took out a 3 first or a 5 first or whatever. Or even if you took out a non-prime first, if you keep going, you'll end up with the exact same prime factorization. So prime factorizations are unique, but you have to go all the way to the primes, right? Like if instead I did, 15 and 105, you're like, oh, that's different, but 15 is not prime, that's 3 and 15. And 105 is not prime, that's 5 and 21. And then 21 is 3 and 7. And I have the same 2 3s, 2 5s, and a 7. So it doesn't matter kind of how you do the subdividing there. You'll end up with the same prime factorization at the end. That is unique. That's actually, that property is actually a theorem. It's called the fundamental theorem of arithmetic that says prime factorizations are unique. So, which is nice, right? This would be enormously difficult if, like, depending on how you did it, you got different answers. Steph.
Mr. Kulik.
We do number 9 on the same page.
Sure. What's up?
Oh, I was going to ask you to do one also.
Okay. Let me get number 9, and then I'll get you next. Okay, Leo?
Yeah.
Which one did you want to look at?
The one I wanted was number 13 on homework 3.
Okay, we'll get that one next. All right, so cube root of negative 750. I'm going to do the same thing. I'm going to do a prime factorization. So already I know I'm going to just be taking out that -1. Okay with that, so I'm just going to worry about the prime factorization for the 750.
Okay.
So I don't know, like 75 and 10 seems pretty obvious. 10 is 2 and 5. 75 is 3 and 25. And 25 is 5 and 5. So if I look, I have 1, 2, 3 5s. And then I have a 2 and just a 3. Now, since this is a cube root, the 5 can come out, right? Because that's a packet of 3. And I know the cube root of -1 is just -1, so that can come out. But the 2 and the 3 that are just to the first power have to stay in there. So if I multiply that stuff all together, then I have -5 cube root 6. Is that okay?
Yeah.
So again, like if you can get to the prime factorization, it's not too bad from there. I'm going to jump to homework 3 and look at, Leo, what number again? Okay.
13, yeah.
Sure. Okay, so my plan here would be starting with a prime factorization. So most of these I'm just going to do in my head. I don't need to draw a factor tree. 9 is 3 squared. 81, or I'm sorry, 2 is 2 to the 5th. And then cube root 2, there's nothing to do there. And 81 is 3 to the 4th. And I don't know what I was thinking when I wrote this one. Anyway, so if I look here at the 2 to the 5th, really I'm going to think about that as 2 to the 3rd and then 2 to the 2nd, which is still 5 2s, right? I've just grouped them into a packet of 3. So that piece can come out. So I'm not going to do anything to that numerator. The denominator, I get that packet, or that 2 cubed. I can pull out a 2. And I'm going to think about the same thing over here. I'm going to think about a 3 to the 3rd and a 3 to the 1st. And then I have a 3, 3. So far, so good? Leo?
Yeah.
Okay. To continue now, what I'm going to do is I'm going to rationalize these denominators. So in each of these problems, the denominator has a radical in it. What I'm going to do is I'm going to multiply the top and bottom of this fraction to get rid of the radical that's in the denominator. Kind of the same idea that we have when we make a common denominator when we add fractions. So for this 2 squared to go away, or this cube root of 2 squared to go away, I need to have 3 2's underneath that radical. So right now I have one more 2 under that radical for it to go away. If I look at the other fraction, I have a cube root of 3. For that cube root of 3 to go away, what I need is 3 3's underneath the radical. Right now I have only 1 3, so I need 2 more 3's under that radical. And it's okay that I'm doing this because when I multiply each of these times, really what I'm multiplying is 1, right? And you can certainly multiply anything by 1 and it doesn't change the value. So I haven't really done anything. I've just, what I'm going to do is make this look a little different, but that's okay. Because these guys are, I'm going to write them so that they're in the same and likewise numerator. So far, so good, Leo?
Yeah.
Okay. Now, if I look at these pieces, the cube root of 2 cubed is just 2. And the cube root of 3 cubed is just 3. So really what I have in this denominator are 4. What I have is 3 times 3 or 9. So now what I'm going to do to add these two fractions is make a common denominator. So the least common denominator for 4 and 9 is just going to be 36, 4 times 9. Over 9 fraction, I'm going to multiply by 4 over 4. Which gives me this. To be able to subtract, to be identical, which they are, each of them is the cube root of 2 times 3 squared. So to do that subtraction, I just do coefficients. So 45 minus 12 is 33. And then I can reduce this fraction a little bit because
2 root 4. I'm pretty sure that's what it would be. Oh, never mind, because it's in a third power.
Yes.
Never mind.
Yes.
Sorry, I answered.
That was one of the hardest things I've asked you to do on these last few assignments. Is this one was, there's a lot to do there, right? And there's really no shortcut through that. That was just, you know, you had to grind through the whole thing. There wasn't any quick workaround or any sneaky thing you could have done. That was just a rough one. Do you guys want to talk about some more from these homeworks? Yes.
Can you please do number 7?
On homework 3?
Yes.
Okay. So this one here, right?
Yeah.
Okay. So I'm going to start with prime factorizations. So 28, 2 squared times 7. 98 is 2 times 7. And I'll make a decision about whether I want to think about that as one big radical or 2 separate radicals in a second, because I want to look at what's going on in here also. 18 is 3 squared times 2. And 50 is 5 squared times 2. And cube root of 8 is 2 to the 3rd. So what I think I want to do is not actually to reduce anything in this first radical, I think it's going to be easiest if I just kind of do my simplifying and then I distribute first. So here in the first one, I have a 2 squared, so I can take the 2 out. In the denominator, I have a 7 squared, so that 7 can come out. Inside the parenthesis, the 3 squared, that comes out. And the 5, so the 5 can come out. And the 2 cubed, I'm going to think about as 2 times 2 to the first. So again, like I have a 2 squared, so that 2 can come out. So far, so good?
Yeah.
Okay. These guys can add because they're the same radical. So 3 square roots of 2 and 5 square roots of 2 gives me 8 square roots of 2. And now I'm just going to multiply this into there. So it gives me 2 times 8, and then 2 times 7. And the denominator is 7 square root of 2. I'm just going to write that as 6 root 2. So those guys can reduce. So I'm left with 16 square root 7 over 7 minus 6 root 2. And notice that these radical parts are not the same, so I can't subtract those even if I wanted to make a common denominator. Really as good as we can do. If you made a common denominator and wrote those as one fraction, that would be okay also, but you don't really need to do it. Is that okay with you, Rochelle?
Yeah, thank you.
You're welcome. Any more takers on one of these last 3 homeworks? Again, happy to do more. The skill that we're working on is quite important, as it's going to be kind of used throughout this chapter. So if we're not able to kind of reduce these radicals, it gets, it's going to continue to kind of get harder and harder until you kind of get this skill straight. Stefan?
We do number 13 first.
13 on homework 1?
Yeah.
Okay. Okay. So once again, what I'm going to do is I'm going to start with a prime factorization. As you guys are probably getting familiar with by now, this is a common starting spot. So 30 is 2 times 3 times 5. And 105 is 3 times 5 times 7. And if I look at each one of those, there's nothing squared in either one. So I'm just going to think about this all under one radical. Is that okay? So if I do that, then I can collect the 3's together and make a 3 squared. I can collect the 5's together to make a 5 squared. So the 3 and the 5 can come out, but the 2 and the 7 are stuck underneath. And then we just multiply things together. And I have 15 square root 14. Is that okay?
Yes.
So again, depending on what your prime factorization looks like, the first step you might want to combine them into one radical. when you're multiplying or dividing. Or sometimes it's like, well, let's think of them as separate radicals first and do some reducing. And maybe that's easier than putting them all together. So it just kind of depends. But I always start with a prime factorization. Walter?
Can you do 8 on homework 2?
Yes. 8 on homework 2. Okay. So much in the same way, I'm going to start with prime factorizations. So I'm going to go ahead and take these 3 coefficients and just kind of stick them together at the front. And then 225 is, I'm going to change color so I don't get confused about what's my coefficient and what's my prime factorizations before I put the radical in. 225 is 5 squared times 3 squared. 60 is 2 squared times 3 times 5. And 500 is 5 to the third times 4. And I'm just going to think about this all under one radical, I think. Will probably be the easiest way to think about it. And what I'm going to do is try to group things together in packets of 3. So I already have 1 5 to the third right there. But I can take that 5 squared and that 5 to the third, and 5 to the first, excuse me, and make a 5 to the third. Okay with that, Walter? I can take this 3 squared and this 3 and make a 3 to the third. I don't know why I wrote that as a 4. I've written that as 2 squared. And then if I think about one of those 2 squareds as like 2 to the first, 2 to the first, I can take like this 2 squared and that 2 and make a packet of 3. Yes, Stefan?
So you're never trying to like combine, when you're multiplying the square roots, you're just trying to make exponents?
That's kind of the way that I think is the easiest way to approach it, is to just, whatever the index of your radical is I'm just trying to make packets of that amount. Because like when I get something to the third, then I can pull that out. If I get some, it doesn't matter what the number is, if I have that number to the third, I can pull it out. And the easiest way to kind of figure those out is just to start with the primes and group them together. Is that okay with what I've done?
Yeah.
Walter, you're still all right? So if I look here, I can pull out a 5, another 5, a 3, and a 2. So I still have that stuff out front. And then I can take out 2 5s, 1 3, 1 2, and I'm left with just the 1 2 left over. Right, where this one is that 5, that's that 5, that's that 3, that's that 2. So then I just multiply that stuff together. So 2 times 3 times 5 times 5 times 5 times 3 times 2 is 4,500, and then cube root of 2.
Can you just bring that 2 down?
So,
the middle?
so this 2 is that 2. Yep. Okay. What do you guys think? Are we ready to talk about the next thing here? You want to ask some more questions? Doesn't mean that you can't ever come back and ask more questions about these homeworks. It's still okay to do that in the future, but if you guys are kind of tapped out for today or just ready to look at something else for a minute, that's okay too. Okay. Of course. Multiplication and division of unlike radicals. So what do I mean by unlike radicals? What if I wanted to multiply the square root of 2 and the cube root of 2? That's what I mean by unlike radicals, right? So the number under the radical is the same, but the type of radical is different. That's what we're going to talk about how to do today. Everybody on board with that plan? Okay. So this is our goal, is to figure out how to deal with this. To do that, we need an alternate definition of what we mean by a radical. So what we're going to do is we're going to give you guys the exponential definition of a radical. So if I have the nth root of a to the m, that's the same thing as a to the m over n. And that's going to be kind of our key, because if we're able to rewrite radicals as exponentials, we now have access to a whole host of properties involving exponentials and how to deal with exponentials. And I'll review what those properties are, but they're things that you would have seen or picked up in your Algebra 1 class, but that's been a little while, so we'll kind of go through those again. But there's, I don't know, like 6 or 7 of them that are particularly relevant for us. So before we do that, though, let's just practice going back and forth. So let's write these in the exponential form. So if we have the cube root of 2, what is the exponent on the 2? It's there, but we never write it. The exponent is 1, right? Everybody's cool with that? So if I follow the definition here, the index of my radical is the denominator in my exponent. And the exponent on the radicand, that's the number underneath the radical, is the numerator. So this is just 2 to the 1/3. Everybody okay with that? What if I have the 5th root of 4? Well, hopefully you recognize that 4 isn't a prime number. So I would start by doing a prime factorization for the number 4. I think we know that 4 is 2 squared. So if I do the same thing, I have 2 to the 2/5. Are we okay with that idea? Let's do one more just to make sure we got it. Let's say we're going to do the 8th root of 16. So again, starting with the prime factorization of 16, that's 2 to the 4th. So the 8th root of 2 to the 4th is 2 to the 4 over 8. which reduces to 2 to the 1/2, which just for the record is the same thing as the square root of 2, right? Remember, the index for a square root, we don't ever write. We understand it to be 2, though. So this is just like as an aside. You guys feel okay going to exponential form? What if we want to go backwards and go from exponential form and write as a radical this time? So let's say we have 7 to the 3/5. So the denominator of our exponent is the index for our radical. So we have a 5th root. And then the numerator of our exponent is the exponent under our radical. And then if I wanted to, I could multiply 7 times 7 times 7. And we could write that as the cube, or the 5th root of 343. Everybody feel okay there? You want to do one more of those? Sure. Sure. So let's say we have 2 to the 5/9. So again, the denominator in the exponent tells me the index of our radical. So this is a 9th root. And then the numerator in our exponent tells us the exponent underneath our radical. And then if I did 2 times 2 times 2 times 2 times 2 into my calculator, or I type in 2 to the 5th, either one is fine, I get 32. So this is the 9th root of 32. Okay with that? So we've seen now how to go back and forth between radical to exponential and exponential back to radical, right? So the nice part about exponential form is that we have a little bit more direction on what to do here, or what we can do with exponentials. So these are some properties that we can use with exponentials. So if I have 2 exponentials with the same base, so in this case, the base is a. When we multiply these together, we add the exponents, right? Like x squared times x to the 3rd is x to the 5th. It's a property that we've used kind of without mentioning that this is a property for a bit. But you feel okay there? And that should be pretty obvious as to why that's true, right? If you have like x to the 3rd, that's x times x times x. And you multiply it to x squared, which is x times x. You just have x times x times x times x times x, or 5x's multiplied together, so x to the 5th. Is everybody okay with that? That one should feel pretty obvious as to why that's true. And if you're ever stuck as like, oh no, do I add the exponents or I multiply? Think about what the definition of an exponent is. And it's usually pretty clear that, oh yeah, that's an addition problem. So the second property is the exponent of a product. So if you have two things multiplied together, raised to the power n, that's the same thing as those things each thing to the power n multiplied together. Which again, if you think about why that's true, let's say we have 2 times 3 to the second. That's 2 times 3 times 2 times 3. So the 2's get multiplied together and the 3's get multiplied together. I have 2 3's and 2 2's, so I have 2 squared and 3 squared. Right? Just as a trivial little example as to why that's true. So the next one is if we have an exponent of an exponent. In that case, we're going to multiply the exponents. So if I do that, just to show you why it's true, if I have 2 squared to the third, that means I have 3 2 squareds. Each of those 2 squareds is 2 times 2. So I have 6 2's altogether. 6 is really just 2 times 3. Okay. Oh, excuse me. Oh. Let's see, what's next? So the next one says if you have a to the n divided by a to the m, that's going to be the same thing as a to the n minus m, which hopefully isn't much of a surprise, right? Because we saw with multiplication, we add the exponents. With division, we're going to be subtracting the exponents, and that hopefully feels like a natural connection between those two things, right? Just to kind of get a feel for it, if I have like 2 to the 5th divided by 2 squared, I basically have 5 2's in the numerator and 2 2's in the denominator. So I can reduce like that, leaving me with just 3 2's, which is exactly 5 minus 2. So again, this is not how I'd use the property. I'm just kind of demonstrating to you why this is true, right? All I'm trying to do is give you a feel for like, oh yeah, okay, so that's obviously that has to be how that would work. Just a little simple numeric example to illustrate why it's true. So the next one is if I have an exponent of a fraction, that exponent applies to both the top and bottom of the fraction, which again shouldn't be much of a surprise. Like if I have 1/2 squared, that's just 1/2 times 1/2. So like 1 squared over 2 squared. Oh yeah. Sure. That's got to be the way that works. We have a to the 0 is 1, provided that a is not 0. So the best way to think about that is 0 is like 1 minus 1, which would be like the property 4, thinking about it as like 2 to the first over 2 to the first, which is obviously just 1, right? That one's a little bit trickier to see like why that would have to be true, but that's kind of the easiest way to think about it. And I think this is our last one. So this is a negative exponent. What the heck does that mean? Well, it means a reciprocal. So like 2 to the negative 1, I can think about negative 1 as just like 0 minus 1. And then using my property 4 in reverse, that's really 2 to the 0 over 2 to the 1. And then using property 6, 2 to the 0 is just 1. So I really just have like the reciprocal, right? So these 7 properties will be super important for you guys. You'll use these throughout the homework along with our definition. So you'll definitely want to, put those someplace that's easy to find in your notes. I'm going to put a big box around it so I can so it's easy to come back to refer back to. Or easy for you to find when you go through my notes. But those will be super important. So let's return now to our goal question for the day, which was multiplying the square root of 2 times the cube root of 2. So the first thing that I'm going to do when I have unlike radicals like this is to rewrite everything in exponential form. So that's going to be 2 to the 1/2 times 2 to the 1/3. Everybody okay with that? That's just using our new definition of of a radical, where I can rewrite it as a rational exponent. I can then use property 1 from my list above to rewrite that as 2 to the 1/2 plus 1/3. To add 1/2 and 1/3, I need to make a common denominator. What would the least common denominator be between 2 and 3? Would be 6, right? Everybody agree with that? So to make that common denominator of 6, I need to multiply the first fraction by 3 over 3, and the second fraction by 2 over 2. So that's going to give me 2 to the 3/6 plus 2/6. Now that we have a common denominator, we can add these two fractions by adding their numerators. So that's 2 to the 5/6. And then I can just translate this back to a radical. So the denominator for my exponent is the index of my radical. And the numerator for it is the exponent inside my radical. Or just the 6th root of 32. Oh. Everybody okay with that? Now maybe that's a little surprising, right? That if I multiply a square root and a cube root together, I get a sixth root. Probably not obvious. You probably wouldn't have thought that's what was going to happen at the start. But that's the power of using them, or using a rational exponent. It allows us to combine any radicals together through multiplication or division pretty easily. Let's do some more examples. So the rest of our time today is just going to be spent kind of running through some examples until you guys feel adequately like I've built up enough intuition for you guys, and then we'll release you to kind of work on some problems doing this. Okay? These first problems I'm going to try to keep fairly straightforward. So like we'll keep all the numbers very small where there's not a lot of prime factorization to do till we kind of get the hang of things. So let's say we have the square root of 2 divided by the cube root of 2. So my first step would be to rewrite these using rational exponents. So that's 2 to the 1/2 over 2 to the... Everybody's okay there? Using property 4, right? Yeah. I would subtract these exponents. So I have 2 to the 1/2 minus 1/3. Again, to subtract two fractions, we need to make a common denominator. Just like the previous problem, this common denominator would be 6. So I'll multiply the first fraction by 3 over 3, and the second one by 2 over 2. That gives me 2 to the 3/6 minus 2/6. Hi, come on in. Am I passing things back?
Community time.
Sure.
PSAT test booklets and hard copies of their scores.
Sure. Right here is a good spot. Thank you, sir.
If there's any issues or kids in the gulag or whatever, let me know. I'll come back and get them.
Okay.
Thank you.
No problem. So if I subtract 3/6 minus 2/6, I get 1/6. And then I can just rewrite that as a radical. That's the 6th root of 2 to the 1st. Everybody okay so far? Things are going too fast, or you're not sure what's going on, please speak up. But I'm trying to go like intentionally kind of slow and deliberately. Grace?
You don't need to write the 1.
Right, if you didn't write the exponent of 1, that would not be wrong. I just put it in there so you can see how I'm using the definition. But certainly the exponent of 1 doesn't need to be there. What if we go and tried this the other way? This is a little... So we'll do it first, kind of what you would obviously do. That turns out to be kind of a pain in the neck. And then I'll come back and show you like what you could have done instead that would actually turn out to be a good bit shorter. But one of the hardest parts about dealing with these rational exponents is, at least initially, you can spend a lot of time kind of chasing your tail inside of a problem, not really getting anywhere, which is kind of a bummer. And there's not like a set order of doing things to avoid having to do that. You just have to kind of do enough of these problems to get a little bit of experience to go, oh, I see what's going to start happening here. I better do this instead. Because at first glance, there's nothing to distinguish why this problem would be any more difficult than the previous one, right? Or any more time consuming, I should say. But it'll turn out that that is the case. So again, translate to exponential form. Since it's division, we'll apply property 4. We'll make our common denominator just like we've done before. It's the same common denominator, so I won't belabor that point. So that's going to be 2 to the 2/6 minus 3/6, which is 2 to the negative 1/6. Everybody okay to hear? Now, if I apply property 7, since I have a negative in my exponent, that's going to give me 1 over 2 to the 1/6. And then I suppose I'd want to translate this to radical form. So that's 1 over the 2 to the 1st. But oh no, we have a radical in our denominator. Fiddlesticks. I remember, as we mentioned previously, we're not going to leave our final answer with radicals in our denominator. So we need to rationalize this denominator. Right now we have a 2 to the 1st underneath that 6th root. How many 2's do I need underneath that 6th root for it to go away? 6, because it's a 6th root, right? I have 1 2. How many more do I need? 5 more. So I'll multiply the top and bottom of this fraction by the 6th root of 2 to the 5th. And the 2 to the 5th is 32. And the 6th root of 2 to the 6th is just 2. So there's my final answer. That was kind of yucky, huh? Now, what I would do differently is at this step, as soon as I see that the exponent in the numerator is less than the exponent in the denominator, I'm going to do something differently, right? 1/3 is less than 1/2. Everybody's okay with that? If the fractions are kind of funky, you can always type them into your calculator to get the decimal, and it's easy to compare. You know, if you had 5/12 and, 3/7, most of us probably would go, I don't know which one is bigger or smaller. Just type them into your calculator to get the decimal and compare the decimal, right? Here's what I would do differently at this step. Is that instead of using property converting these into rational exponents and using that property 4, I'm just going to rationalize the denominator right now. So I'm going to just multiply the top and bottom by square root 2. So the denominator just becomes 2, right? And this is exactly what we did in part A. Right? Cube root of 2 times square root of 2. And I'd be done. Mr. Kulak, that was so much quicker. Well, part of it is I was able to recycle work that I've already done, which is always nice, right? We'd like to be able to do that whenever possible, because I don't know about you, but I'm not about like recopying things that I've already done. Once is enough usually for me. You know what I mean? And the second is that really I was able to skip like all of these steps because I didn't really need to do any of them. Like me rationalizing the denominator is really where I started from and then did some simplifying after that. But like, to me, that felt a lot easier to do it that way, or a lot quicker to do it that way. But here's the great part. If you don't catch that, it doesn't matter. You still get the right answer. You just maybe take the scenic route to get there. But that's okay. There's nice scenery on the scenic route. You get to learn a bunch of mathematics along the way, which is not a bad deal. D is the next letter in the alphabet. So let's make these problems a little bit more complicated because we'll use some more some non-prime numbers in this. So let's say we have the cube root of 12 times the 4th root of 54. So here I'm going to start with a prime factorization. So 12 is 2 squared times 3. And 54 is 2 times 3 to the 3rd. So when I'm doing this, I'm really drawing those factor trees, right? Because I'm doing this problem, I'm just doing the factor tree in my head. If you can do those in your head, you're welcome to do that, or do them on your calculator, or draw the factor tree, like whatever works for you. But that's ostensibly what I'm doing. I'm just doing it in my head. You guys are okay with that? When I just write the prime factorizations up like that? Okay. So next thing I'm going to do is convert these radicals into exponents. Everybody good with that? So now I have an exponent of a product. That was our property 2. That's going to be 2 squared to the 1/3, 3 to the 1st to the 1/3, 2 to the 1st to the 1/4, and 3 to the 3rd to the 1/4. Everybody okay there? Now if I look, I have property 3, the exponent of an exponent property, happening 4 times, right? So I have 2 to the 2 times 1/3, and then 3 to the 1 times 1/3, and then 2 to the 1 times 1/4, and then 3 to the 3 times 1/4. To multiply fractions, I just multiply the numerators together and the denominators together. So all of these whole numbers I'm just going to think about as like whatever over 1. So that gives me 2 to the 2, 3 to the 1/3, 2 to the 1/4, and then 3 to the 3/4. Is that okay? So I notice here I can multiply these together by property 1 because they both have the same base, that being 2. And I can multiply these together by property 1 since they have the same base, namely 3. So using property 1, I have 2 to the 2/3 plus 1/4. And I have 3 to the 1/3 plus 3/4. Everybody okay that? To add these fractions, we have to have a common denominator. The least common denominator between 3 and 4 is 12. So the first fraction, I'll multiply by 4/4. The second one by 3/3. So that's going to give me 2 to the 8/12 plus 3/12, and then times 3 to the 4/12 plus 9/12. So if I add those together, I have 2 to the 11/12 times 3 to the 13/12. And then to convert those back to radicals, I have the 12th root of 2 to the 11th times the 12th root of 3 to the 13. But I noticed that 13 is bigger than 12, right? So I could really think about this as 3 to the 12th times 3 to the 1st. Everybody see that? So I do have a packet of 12 there. So I can take that 3 out. Stick that out. And then these are both 12th roots, right? So they can go back together into one packet. And if I wanted to, if I type 2 to the 11th times 3 into my calculator, I get 6,144. And that's as good as I can do. So you can see here that these can get kind of complicated. Now I'm showing a lot of work, a lot of steps here. I'm only doing one property per step. I would encourage you guys to kind of do the same thing when you're first starting out. These problems can get, can be a lot of steps, and that's okay. I'd really rather you start off trying to do one step at a time than trying to combine a bunch of stuff together. At least for this first assignment, when we come back and revisit this topic next time, and we do some questions, I'll kind of talk about start combining some of these properties into more than one step to cut down on the amount of work that we have to show. But until you feel comfortable using these properties of exponents, really try to do them just one at a time. It'll make things it'll keep things from getting too confusing, I think. So if you look at the OneNote, in the content library, you should see homework 4. I put that in there this morning. So the first 3 problems, we're just going to take exponential form and convert them to radicals, and then from radicals into exponential. And then I have some simplified